Hi everyone, in this video we're going to be talking about section 10.2, which is on infinite series. So if you remember from the last video when we first mentioned what chapter 10 was about, series and sequences, the difference is for a sequence you're listing terms, there's commas in between. A series you're adding terms. Technically it could be subtracting also, some of them are negative, but you're adding, so you have plus signs in between. And so an infinite series is the sum of something, and if you recall, the sequence has the list of the terms, so you're just adding the terms from the sequence. So it's the sum of an infinite sequence. Infinite sequence. Okay, so that's what we are calling an infinite series. So for example, just in general, here's the terms of a sequence, a sub 1, a sub 2, and so on, and because I'm adding them, that's why we call it a series. Notice it's infinite because it keeps going. And then the sum of the first n terms, well, that's a little different because we want to stop somewhere. So that would be like me stopping this sum right here. So if I want to just say the sum of the first amount of terms, some number of terms, well then that looks like this. S sub n is our notation for that, and it would be the first few terms, however many n is, wherever you want to stop in your list. So a sub 1 plus a sub 2 plus so on until you decide, okay, this is my last one. Maybe this is the 5th term, maybe this is the 100th term. This is the sum of the first n terms, and what we call it is the nth partial sum. Okay, it's a partial sum because this is technically an infinite sum. You would be adding infinitely. Now, the partial sum is when you actually stop. So it's part of the infinite sum, and then you stop at whatever number n is. So let's take a look at one of these examples. Alright, taking a look at this example, we have 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus so on and so on and so on. So this is an infinite series, and what we're going to try to figure out, and I'll walk us through it, is a formula for a partial sum for the series. So for any n value that we choose, is there a formula to find the sum of those terms? So for example, if I add up the first 3 terms and I get some value, is there a formula for that? And does that same formula hold for if I add up the first 4 terms, or the first 5 terms, or the first 1,000 terms? And so we'll work our way to that formula. We're going to find it. So let's start by adding terms one at a time and looking for a pattern. Okay, this is one of the processes that we'll go through for this type of thing where we're looking for this formula. So I'm going to say the first partial sum. So it would be denoted S sub 1, and we would call it the first partial sum, or the sum of the first 1 terms. And so in this case it's just 1 because that's the only term. So the value of that partial sum is 1. Let's go to something more interesting, the second partial sum, or the sum of the first 2 terms, 1 plus 1/2. Okay, if we add that up, we're going to get 3/2. Let's keep going. You basically keep going until you can start to see something you can work with in terms of maybe a pattern. So then the 3 terms being added, the first 3 terms, the third partial sum, 1 plus 1/2 plus 1/4. If we add that up, we get 7/8. And this might be good. Maybe we can figure it out from here, but I'm going to just do one more and then generalize it. So let's do the fourth partial sum, sum of the first 4 terms, 1 plus 1/2 plus 1/4 plus 1/8. Okay, and that becomes 15. Oh, sorry, this was 7/4 back here. 7/4, and this is 15/8. Okay. Now let's go to the nth partial sum. So now I'm going to start generalizing it. So I'd say like dot 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 S sub n. It's my same first few terms, and then I have an nth term. Okay. Now I picked this example because we don't actually know how to find the nth term. So sometimes with sequences that you're working with, you do know how to find the nth term. Maybe it's like really clear, or you have a formula already given for you, some kind of a sub n formula. But this time we don't. So the very first thing we have to do before we can even consider a formula for a partial sum is, well, how do I generalize the terms in this sequence? How do I generalize this series? Okay. So the terms in this sequence, let's see if we can just talk through it and figure it out. Remember what the term number is. N is the subscript, and it represents each term number. So this first term means n is 1. The second number means n is 2, and so on. N is 3, n is 4. Okay, so what you always are trying to do with sequences, because remember, sequences are how we get these terms. Series is when we add them up. Whenever you're working with sequences and you're trying to find the formula for them, for like the nth term, one thing you can do is identify what a relationship between the term number, like this number 1, and the output 1. Number 2 and the output 1/2. Number 3, the output 1/4, and so on. So I do want to pay attention to my term numbers. Okay, so let's see what we can figure out. Now, there is something interesting about the denominators, and when I show you this for this first one, you'll start to see it repeated in other problems. When you have a 2, a 4, and then it jumps to 8, and then it jumps to 16, you'll see this enough in math that you'll start to recognize what it is. It's actually powers of 2. So I'm going to rewrite our series up here in terms of powers of 2. I'm even going to start with the very first number. 1 is the same as 1 over 2 to the 0 power, because 2 to the 0 power is 1. So this is 1 over 1. The next term is 1 over 2 to the first power. That's the 1/2. Then 1/4, this is 1 over 2 squared. This is 1 over 2 cubed. This is 1 over 2 to the 4th. Okay, so when you see these numbers, when it doesn't go like 2, 4, 6, 8, notice how 6 got skipped, and then it jumps all the way to 16. It's not just even numbers, it's actually specifically powers of 2. Alright, now I'm going to re-put my n values next to this to see if I can come up with some kind of relationship. Again, we're not quite on the partial sum factor of this question, of this idea that I'm trying to show you. We're actually at the beginning step where we're trying to figure out, how do I just figure out the terms in this sequence? So this was the very first term, so n was 1. This was when n was 2, n was 3 here, n was 4 here, and n was 5 here. Alright, so what you're looking for is some kind of relationship between your terms and your n values. And hopefully you see it. Are you seeing what I'm seeing? The power here on 2 is always 1 less than this number. So when n was 3, this power was 2. When n was 4, this power was 3. When n was 5, this power was 4. Okay, so that's good. We recognize that, and that's going to help us write our nth term. And so in general, my very next term, in general, the nth term should be my n value as my exponent, but 1 less. So 2 to the n minus 1. Okay, so I'll put that here. 1 over 2 to the n minus 1. And then notice on this one, I would actually keep going if that's my series. It's infinite. But on this notation, I'm stopping because this is a partial sum. I'm stopping at n, whatever term n is. So over here, this is n equals n. Okay. So that's like the preliminary step. We found a way to write about the nth term in general. Now we're looking for this part, a pattern for the partial sums. Because what if I want to add the first 100 terms of this series? I don't want to just add them by hand or with the calculator. Is there a formula for it? And that's what we're finding. And so the formula, we have to relate the way that the partial sums look when we write them term by term with the value that they've outputted and see if there's some kind of relationship. And so let's look at these values now. 1 is not very easy to work with. There's no details here. So let's start with the next one. 3 over 2. Okay. The next one, 7 over 4. 15 over 8. Notice the denominators are all powers of 2 again. Okay, so let's see if we can rewrite these values that we got out of our partial sums with powers of 2 mentioned in the denominator. So this is 3 over 2 to the first power. This is 7 over 2 to the second power. This is 15 over 2 to the third power. Alright, now if you saw this and you couldn't see a pattern yet, like I have no clue what to write for the number on top specifically, then you could keep going. You could say the 5th partial sum, s sub 5. But I'm going to have us figure it out from here. This is actually enough to figure this out. So, from here, let's see what we can come up with. If I look back at the way my partial sum is written, I can say that this is going to have a common denominator if I use the largest power of 2. So I'm kind of just walking us through the logic here. Let me go back one. Let's go here and figure out if we need to have a common denominator here. Does that help us? And I'll just tell you, it's going to make it more complicated. Okay, but you'll see where I'm headed. And it's actually easier to work here. Because this is sometimes the process you go through when you're working with these things, these series or sequences. You really don't know what the formulas are and you just troubleshoot. You just try a few things. Okay, so if I go back here, the common denominator would be 8. So 1 is 8 over 8. So I'm just kind of moving to the side to work. So the 4th partial sum, 1 is 8 over 8. 1/2 is 4 over 8. 1/4 is 2 over 8. And 1 over 8. Okay, so why I did that, that's actually how I found out that this was 15/8, is to see if I can recognize a pattern going on top, on the numerators. Okay, so we already know that the denominator can be written as 2 to the third power in this example. Well, this is a power of 2. Okay, that's 2 to the third on top. That's a power of 2, 2 squared. This is a power of 2, and technically that is also. And those are all over the same denominator of 2 to the third. So I could generalize this version of it, of my partial sum, and I could use n's here. Remember, n was 4 here. So I could say something like, okay, this is 2 to the n minus 1, since n was 4. Okay, remember that was a 4, so 1 less. Okay, so I could generalize this and say, that's 2 to the n minus 1. 3 is also n minus 1. But then I would have to start saying something like this. Okay, and again, this is actually not the best formula here. I'm going to give you a better one. This is 2 to the n minus 2. That's how I'm going to get a 2 there. This is 2 to the n minus 3. And then so on all the way until I get to 0 for the power. N minus 3. And then in general, I could say that this is 2 to the n minus n. Okay. This technically would work. This could be a formula for our partial sums, our first n terms, if I wanted to add them. This is a really ugly formula. We don't want to use this. So let's see if we can just focus here and see if there's a better way to write this version of our formula. How can I figure out something to do with 15, 7, and 3 based on n? Remember, you're always thinking about the term number, n. So reminding you, this value was when n was 2, this value was when n was 3, and this was when n was 4. Well, my hint for you is that we've already been looking at it. It has to do with powers of 2. So if I'm thinking about powers of 2, and what's 2 to the 4th power? Okay, well, let me just make myself a note. 2 to the 4th is 16. Okay, well, what's 2 to the 3rd power? 2 to the 3rd power is 8. What's 2 to the 2nd power? 2 to the 2nd power is 4. And then with that in mind, look at our values, the numerator values. 3, 2 to the n was 4. 7, 2 to the n was 8. 15, 2 to the n was 16. So if you see it now, these are all 1 less than 2 to the n. Okay? 1 less than 2 to the n. So now what we're seeing is this is, let me see if I could squeeze it in here actually. Let's erase this. Okay. I'm going to erase that s sub n as well. This is 2 to the second power minus, not up there, minus 1. Okay, that was 4 minus 1. And then this is just still 2 to the first power. This is 2 to the third power, take away 1. Still over 2 squared. This is 2 to the fourth power, take away 1. Still over 2 cubed. And this, hopefully you see it, this is a pattern, and so you can generalize it down here for our S sub n. This looks like, okay, n, remember, we already figured out the denominator, you need n minus 1. So this is 2 to the n minus 1. So this number is 1 lower, but our term number was 4 here, and that power on 2 was 4. So S sub n, this is 2 to the n minus 1. Okay, and we can actually make this look even slightly better than the way I wrote it, but this is a general formula for our nth partial sum. Okay, I know it took a while to get there. I honestly walked us through it this way just so you can see the process. Especially when you're working these out for the first time, it kind of goes like that. You're just looking. You're looking for patterns. You're trying things out. So let's make this look a little bit better. You can separate the terms. You could say this is 2 to the n over 2 to the n minus 1, minus 1 over 2 to the n minus 1. If I just separate the terms in the numerator over the denominator. And using your rules of exponents, you can subtract the exponents when the bases match. So n minus n minus 1. So this is, I'll just write it down here. This is, the exponent is going to be n minus n minus 1. So that's going to be 1, positive 1. So this becomes 2 to the positive 1, which is just 2, minus 1 over 2 to the n minus 1. And that is a formula for our partial sum, any partial sum we choose. Alright, so I know it took a minute to get there, but you can use this instead of trying to do it like this. Okay, we can verify. So let's just verify with one of them. We know that for the fourth partial sum, the output is 15/8. So let me give us some room here. Okay, so the fourth partial sum, we don't need that anymore. Okay, so for the fourth partial sum, let's plug in what we know, and the fact that we know n is 4. Okay, so we already know the answer. It should be 15/8, but let's verify with our formula. When n is 4, what are we going to get out of here? When n is 4. Okay, so 2 to the 1, 2 minus 1 to the 2 to the 4 minus 1 power. Okay, so this is 2 minus 1 over 2 to the third power. So this is 2 minus 1 over 8. And common denominator, this is going to be 16/8 when you have a common denominator. So 16/8 minus 1/8 is 15/8. So our formula does work. Okay, so if you ever need to find a partial sum formula, this is the process for finding it. Sometimes you'll be given the formula for the partial sum and then you just plug in n. So if I gave you this formula, you would have started right here. You wouldn't have had to go through all that. Alright, so let me give you one last definition, and then in the next video we'll look at some other examples. Alright, our last definition here. We've already talked about part of what's on the screen. We know what an infinite series is. It's when we're adding up the terms of a sequence. And so the new part here is just what it is, a sequence of partial sums. So notice the notation. We have our partial sum notation, S sub n, but it's inside these squiggly braces. And so that's actually representative of a sequence of partial sums. So it would be the sequence containing the individual values of the partial sums up until some n term. Okay, and then down here we also have this fact. If the sequence of partial sums converges to some limit, then we can say that that series converges. And that when you add them up, you add up the terms, you get L. You get this limit. And so notice what this is saying right here. If you add terms of your series, starting at term 1 all the way to term infinity, you just keep adding. And if you get a value, some number value L for that series, then we know that that series actually converges. And then, of course, like with sequences, but from before, If a sequence of partial sums of the series does not converge, then we say that it diverges. All right, that's it.